Hello, everyone. I want to start by thanking the VI grade team for having me here to present at this virtual conference. I'd also like to acknowledge my co-authors on this paper, Mark Stickler and Rick Lucan. So we are with Powertrain NVH at Ford Motor Company in Dearborn, Michigan. So I'll be talking about how we use a desktop simulator to improve Powertrain NVH development efficiency. So first, I'll give a little bit of an introduction to the NBH Simulator. With traditional vehicle NVH evaluation, we have several limitations. The first is that vehicle prototypes are very expensive and they're not available in the early stages of a new program. Even when we do have prototypes, performing back-to-back evaluations is very difficult, and it has limited effectiveness in part because of our short auditory memories. So if you have two vehicles you're evaluating back-to-back, by the time you finish evaluating the first vehicle and you're getting into the second vehicle, you've likely forgotten what that first vehicle sounded like. It's also very difficult to configure a vehicle to deliver exactly the sound that you're targeting. And performing what-if studies is difficult and time-consuming. You have to come up with prototype hardware, get it installed in the vehicle, set up an evaluation at the test track, and so on. So the desktop NVH simulator can help overcome a lot of these limitations. It allows for interior sound assessment in a virtual vehicle environment. So you have much of the interactivity and the context that you would have driving a real vehicle. You can build and drive new models well before prototypes are available. You can do real-time back-to-back comparisons. So you can switch back and forth between models that represent different hardware configurations. Maybe it's a competitive vehicle, and this really allows you to highlight the difference in sound. So using these models, we can set and evaluate targets very early in the process at the vehicle level or the subsystem level. And we do this by incorporating subsystem level data from testing. It could be from rig tests, vehicle tests. It could also come from CAE. We incorporate this data into the models. So the picture here is showing our Ford Powertrain NVH simulator lab in Dearborn. So this is a Brule & Care NVH simulator system, which is now part of the VI grade product line of simulators. You can see there's a multi-monitor setup to display the visuals. We have a steering wheel and pedals, allowing you to drive the virtual vehicle, and several sets of headphones to listen back, and multiple people can listen simultaneously. So at Ford Powertrain NVH, we are using a source path contribution approach to build up our simulator models. So this is what we call a level 3 model. And the process involves taking powertrain subsystem level data, which could come from dyno testing, from vehicle testing, or from CAE. We combine that source level data with transfer functions representing the vehicle, and that gives us the interior noise contribution. So for example, if we look at the block diagram in the bottom here, for our power plant mount structure-borne contribution, we would start with active side vibration, mount vibration measured in a powertrain dyno test. Maybe it comes from CAE. We multiply by our estimated mount stiffness to get mount attachment forces. We then have a vibroacoustic transfer function of the vehicle. So this comes from a surrogate vehicle test, possibly from CAE, and that gives us the total interior noise contribution of the power plant mounts. Likewise, for an airborne source, we can take our source level data, combine that with an acoustic transfer function to get the interior noise. So the figure at the top left here shows the components of our typical level 3 model used for powertrain NVH development. So the powertrain sources that we would include are typically the power plant mounts, structure-borne contribution, power plant radiated noise, air induction system noise, and exhaust tailpipe orifice noise. So in addition to these powertrain noise sources, we include masking noise from the road, wind, and tire. So all of this, the noise is synthesized based on a vehicle performance model. So the real-time driving conditions are governed by this performance model, which can be free driving or predefined fixed driving maneuver. So the way the simulator works here is it takes the source level data the time signals, and it decomposes it into harmonic and masking components. So those harmonic components are related to the rotational speed of the engine, and the random noise is everything else. And the noise is then resynthesized in real time based on the driving conditions governed by this vehicle performance model. So fixed driving maneuvers could just be a full pedal acceleration, for example, or maybe a fuel economy drive cycle. With a free driving model, the vehicle will respond to pedal inputs and shift through the gears and so on. So at Ford, we can take from a library of powertrain source and transfer function data to build up new models very quickly using surrogate data. So as we were developing this approach, we wanted to validate it. We wanted to build confidence, convince our colleagues and other members of cross-functional teams that this approach could be used early on to help make decisions. In order to do this, we took a production level vehicle and we built up a level 3 model using the source path contribution approach that I just described on the previous slide. And in parallel, we built a model using direct interior noise measurements. So we took that production vehicle on a test track, measured interior noise. This is what we call a level 1 model. So we had these two models of the same vehicle, one essentially synthesized noise starting from source level data, and the other one a direct interior noise measurement. We set up listening evaluations to have participants listen to the two models back to back. We didn't label the models. And what we found was that the evaluators could not distinguish which one was the synthesized noise built using the source path contribution approach and which one was the direct interior noise measurement, or the level 1 model. So you can see from the objective data at the bottom here, the overall loudness of those two models is very similar. On the right side, we see a comparison of the spectrograms from the level 1 direct interior measurement and the source path contribution approach level 3. So the order structure is similar. There are some differences, however. This could be due to the fact that we didn't have all paths represented in our level 3 model. We also had different powertrain specimens used for these two different modeling approaches. So there is some subtle differences. There are some subtle differences in the sound character here, but they sound pretty similar. So I'm going to play a couple sounds here back to back, and hopefully this comes through okay for you. The first sound is the level 1 model, which is the direct interior noise measurement. And the second sound that I'll play immediately after that is the synthesized sound from the source path contribution approach. So hopefully that came through okay, and you would agree that they sound very similar in character. So the desktop simulator can be used throughout the vehicle development process. So if we consider some generic development milestones, for example, very early on when the program is just a concept, you could use the simulator to evaluate the sound character of a 4-cylinder engine versus a 6-cylinder engine. And that could be important if the NVH is a critical attribute for that program. Where we tend to focus our efforts at Powertrain NVH at Ford is in this phase after the program officially kicks off, as we're trying to align on targets and lock in designs to meet those targets. There's a lot of opportunity to use the simulator to help make these decisions early on. And in the ensuing slides, I'm going to cover several examples in detail. So I'm not going to read through all the text in these boxes here. We'll talk about that in detail in just a minute. But even after prototypes become available, there's still opportunity to use the simulator to avoid having to do physical vehicle testing and evaluation. So as I mentioned, using the simulator helps enable decisions very early in program development before prototypes are available. And this helps reduce expensive late engineering changes. And obviously, as we're reducing our physical vehicle testing, that's an efficiency enabler. There are other uses of the NVH simulator, which aren't discussed in detail in this presentation. So those would include virtual sign-off drives, where you have some models of competitive vehicles that you can drive back to back with your virtual prototype. You can evaluate various powertrain control strategy and calibration options. So for example, with a hybrid electric vehicle with CVT type transmission, you could evaluate different methods of controlling the engine speed and load and how that impacts the NVH. You can also use the simulator to help with sound design. So active noise control and electronic sound enhancement, and especially with the electrification of powertrains, this is becoming more and more important. So now I'll go into several examples detailing how we've used the simulator. So this example shows how we use the simulator to select an exhaust system very early on. So this is for a full-size pickup truck with a V6 engine. And a bit of background here. The engine horsepower was being increased, and in order to enable that, exhaust system back pressure needed to be reduced. So to reduce the back pressure, the pipe diameters in the exhaust system needed to become larger. And that increased the risk for objectionable low frequency tailpipe noise. And we're limited in how large we can make the mufflers to help attenuate that noise due to the underbody package environment. And we are especially package limited for the hybrid electric vehicle variant due to a high voltage battery. So the approach using the simulator was to actually come up with several different candidates, exhaust system candidates, and have prototype parts built up for these exhaust systems. The prototypes were mated to an engine and tailpipe noise was measured. We then took that measured tailpipe noise and incorporated it into a simulator model of the new truck. And we performed listening evaluations to determine the acceptability of the various configurations. So in this first phase of the study, it was determined that configuration B, which is represented by the green line here, was acceptable. So even though this one was not the quietest of the four systems, that was actually the blue curve, configuration C, configuration B was lighter and more package friendly. And so this was selected for the base gas variant. The other thing that came out of the study was that exhaust configuration D, which was the pink line and the loudest of these different systems, was unacceptable for booming noise. So unfortunately, this was the only system that could package in the hybrid electric vehicle. So a second phase of the study was kicked off to try to improve upon exhaust system D using CAE. So through some CAE optimization and predictions of the tailpipe noise, eventually an acceptable configuration for interior noise was found. So exhaust system F was chosen for the for the hybrid electric vehicle variant. So this example, I think, highlights how we can use the simulator to make decisions like this very early on without having to rely on vehicle testing. This next example is discussing how we use a simulator approach for a battery electric vehicle. So in this case, we had some concerns about structure-borne electric motor whine. So we had some CAE analysis of an electronic drive unit. The CAE model was predicting mount vibration, and there were several different structural design features being considered for that electronic drive unit. And so what we wanted to do is use the simulator and listen to the structure-borne whine in the context of the full vehicle. So when you add in the road, wind, and tire and wind masking noise, could you really hear the structure-borne whine noise? So these CAE predictions of the mount vibration from the electronic drive unit were combined with estimations of the mount stiffness and a vehicle vibroacoustic transfer function to predict the whine levels. So we conducted listening evaluations of the interior whine noise with different combinations of structural features of this electronic drive unit. So just feature A by itself, which was heavy ribbing on the motor housing, was deemed unacceptable. So this produced unacceptable levels of whine during a light acceleration event. However, when we added stator reinforcement, so features A and B together, the whine noise became acceptable. And so this was selected as the design direction. So features C and D did not appreciably improve the whine noise, and it was decided to reconsider those later if needed. In this next example, we were considering an air induction system for a small pickup truck with a 4-cylinder engine. So we had a target for air induction noise, second engine order air induction noise. However, there are some questions about how appropriate this target was, and of course there's always a desire to come up with the most cost-effective design. The baseline design performance is shown by the red curve. There was actually 2 resonators in this baseline design, as shown in the picture here. By removing one of the resonators, the cover resonator, you can see that the noise level actually increased and exceeded the target for the induction noise. However, we wanted to see if this really made a difference for vehicle interior noise. So these CAE predictions of the air induction noise were incorporated into a simulator model for this truck, and listening evaluations were conducted. And the result of that evaluation was that the sound was deemed acceptable without the resonator. So the decision was made to go ahead and delete that resonator, saving $1.30 per unit and over $200,000 in tooling. So again, we see here how the simulator can help make a decision and in this case achieve a cost-reduced design without the need for any hardware evaluations. In this last example, it actually applies later on in the development cycle. So here we actually had vehicle prototypes available, but when we measured a near production level engine in a power plant dyno cell, what we found was that the radiated noise had actually degraded quite significantly from the previous design level. This was due to a change to the intake manifold. So we wanted to avoid having to make a change to that intake manifold at a very late stage, revert the design to improve the radiated noise. But we also didn't want to go through the trouble and take up prototype time by retrofitting an existing prototype with this new intake manifold. So we decided to use the NVH simulator. So what's shown here with these curves is the engine level radiated noise, and we're looking at an equivalent articulation index. So higher is better on this plot. You can see the status of the near production level engine is the green curve, which has degraded significantly relative to the previous design level, the blue curve, and is deficient to the target, which is the red curve. So we took these engine level radiated noise measurements, incorporated them into the simulator model, and conducted listening evaluations. And the outcome was that although there were some slight differences in the sound character, both levels of engine radiated noise were deemed acceptable in the context of the full vehicle. And so it was agreed not to make any change to the intake manifold. The target was essentially deviated to the current status. So this decision was facilitated without the need for any physical vehicle evaluation. The last thing I'll talk about is performance modeling. And so we did run into some limitations very early on in this process with building free driving models and getting realistic driving behavior. So with some of the more complex powertrain control strategies and torque converter dynamics, these couldn't always be represented well with the included simulator performance modeling tools. So the solution here was to use a Ford in-house tool called VMAPS, which is a high fidelity simulation tool of the powertrain control strategy and includes detailed models of engine, transmission, and the vehicle. So by running this VMAPS model for performance simulation in real time and having it linked to the NVH simulator, the two software tools were exchanging information and we were able to get very realistic free driving behavior. So a couple examples that I've shown here are the torque converter dynamics. So during a third gear wide open pedal launch, you can see the engine speed has this characteristic stall range due to the torque converter dynamics. So we're able to pick that up very nicely by incorporating the VMAPS model. The example on the bottom is showing, the red curve is showing the gear state for the transmission. So this is a 10-speed transmission. So during a moderate acceleration event, the shift schedule actually calls for skipping some gears. So you can see we went from first gear to third gear and from third gear to fifth gear. That was enabled by the VMAPS tool. And the downshifting logic is even more complicated. So this really opened up some more possibilities with free driving. So in conclusion, we've shown that level 3 simulator models that we construct starting from the powertrain source level data, combining that with transfer functions to get contributions, exhibits very realistic sound character. It's accurate, similar to direct interior noise measurements. So we have confidence in using this approach to make decisions. The context and interactivity provided by the simulator really enhances our decision-making capability. So if we compare that just to looking at lines on a graph, it's just a much more powerful tool to help convince a cross-functional team to make a decision. And it's a lot easier than performing evaluations on the road. So we're getting some significant efficiency improvements by helping to align on these decisions much earlier in the design development process to avoid late engineering changes, which tend to be very expensive. We're also minimizing the amount of physical vehicle testing and validation that we're doing. So in the future, we hope to improve our capability to simulate tonal noises and impulsive noises. So tonal noises are becoming more and more important with powertrain electrification. We also continue to improve our model build and data processing efficiency to increase our modeling throughput. So we'd like to do more and more with the simulator. And finally, at some point, we would like to extend our simulation capability to include vibration. So right now, we just have the interior noise simulation, as I've described in most of these studies. So adding in vibration would add more realism and allow us to evaluate additional error states. So that concludes my presentation. I want to thank you all for your attention